Okay, so we just finished up talking about this example where we had 120 grams of water, and we used the molar mass to relate the grams of water to the moles of water. That's what molar mass is for. So here we can see that 1 mole of water is 18.02 grams of water. Those are two ways of saying the same thing. That gets us from grams of water, which cancel here, to moles of water. And then next, we wanted to know, well, how many actual molecules is that many moles? And whenever we're going between how many moles and how many of the thing it is, we use the definition of what the word mole means. The word mole means this many things, in the same way that a dozen means 12 things. So we can see here that the bottom and the top of our conversion factor mean the same thing. 1 mole of water is this many waters. And that gets us to how many waters we have. Specifically, how many water molecules. That may or may not actually be explicitly written, but if I write the formula H2O, I expect you to know, oh, that is a molecule because it is a covalent compound. How could I tell that this is a covalent compound, by the way, H2O, by looking at the formula? It has only non-metal atoms, right? So I'll try to give you guys a chance to respond. I hope someone will, but if not, I'll just answer my question here, and that is that, yeah, this is water. It's made with hydrogen and oxygen atoms. They're both nonmetals. So the goal of getting the molar mass is to be able to interconvert between grams and moles. And again, that's what counting by weighing is all about. Because we can't count out individual molecules because they're too small to count, instead, what we do is we weigh them, and we have, based from the periodic table, a relationship between how much something weighs and how many moles of molecules or atoms or whatever that is. So here we have an example with an ionic compound. This is called calcium chloride. Hopefully you guys are still good at doing that from the last exam. How can I tell that this is an ionic compound? It has to do with calcium. Metal and non-metal. Yeah, all right. Like, I always ask that question, right? Because it's really important. It's a really important question to ask. If something's ionic or covalent, the way the atoms are bonded is very different from each other. And I do have a note about this, is that, okay, we calculated the molecular mass for water, the mass of 1 mole of molecules. It's important to remember that ionic compounds don't have molecules. They just have positive and ions stuck together. So we don't end up calling this a molecule. What we call it usually is a formula unit. So if you see the word formula unit, it's basically the word that's like molecule, but it's for ionic compounds instead. And often we call the molar mass for a molecule the molecular mass. For ionic compounds, we'll often call the molar mass the formula mass. These both mean molar mass. So if I go back to the first slide, I pointed that out, that little bit of terminology here. Yeah, so molar mass, if we're doing it for an ionic compound, might also be called formula mass. If we're doing it for a covalent compound, it might be called the molecular mass. But both of these are covered by the broad term molar mass. Okay, so let's go back to the slideshow and talk about how we're going to calculate the molar mass for calcium chloride. Yes, metal and non-metal. Good. Okay. So, so let's say we're going to calculate the molar mass of calcium chloride. Well, we need to know what's in the calcium chloride. So this goes back to counting atoms like we did when we balanced. If we have 1 calcium chloride, this has 1 calcium atom, and then it has 2 chlorides. So if I'm writing here on the slide, if I were to write this out, calcium chloride, as a as an ionic compound? Well, it has 2 calciums, which are 2 plus, but we don't really care about that right now. And it has 2 chlorides, which is -1, but it has a second one, 2. So this calcium chloride has altogether 1 calcium ion, and then it has 2 chlorine atoms in the chloride ion, and it has 4 oxygen atoms. Remember the way we get that from balancing equations. 1 times 1 is 1 calcium atom. 1 times 2 times 1, that's 2 chlorine atoms. 1 times 2 times 2, so 1 of these, we have 1 of these, times 2 times 2, that's 4 oxygen atoms. That's because there's 2 chlorides and each one has 2 oxygen atoms. So that's 4 oxygen atoms total. So if we have 1 of these, we have 1 calcium atom, 2 chlorine atoms, and 4 oxygen atoms. If we have a mole of calcium chloride units, we have 1 mole of calcium atoms and 2 moles of chlorine atoms and 4 moles of oxygen atoms. All we did was scale this up to a mole. Now that concept is difficult because it's hard for us to imagine how big a mole is. A mole is a lot of things. However, we can always scale it up this way. If we can count how many they are one by one, we just scale it up to a mole. Okay. So now we know we have 1 mole of calcium atoms and 1 mole of calcium chloride. And a mole of calcium weighs 40.08 grams. Again, your periodic table is going to be really useful here. And I'll show you here for calcium. If we want to know how many grams a mole of calcium atom weighs, we go to the periodic table, we find calcium right here, and it weighs 40.078 grams. Now, often you don't want to use all these numbers. Some of these have a lot of numbers written after them. Use as many as you will need, depending on your data. So we don't really know what our data is yet because we haven't started a problem. We're just calculating the molar mass. So I'm just going to kind of default to going 2 after the decimal place. So I'm going to write 40.08. I rounded the 7 up to an 8. Okay, so that's what you see right here, 40.08. I'm going to do it for chlorine as well. So we have 2 moles of chlorine. Each one is 35.45 grams per mole. If we go to chlorine, chlorine is all the way over here. And the mass of 1 mole of chlorine atoms is given right underneath. It's 35.45 grams. Okay, so that's what we put here. And we've got 2 of them because when we count these, 1 times 2 times 2, that's 2. And so we multiply the mass of 1 mole of chlorine atoms times 2 since we have 2 moles. So we get the mass of our 2 moles of chlorine atoms. Now we have 4 moles of oxygen atoms. So that's 4 times 2, or sorry, 1 times 2 times 2. That's 4 moles of oxygen atoms altogether. Each one of those weighs 16. If I go to my periodic table and find oxygen, it's right here. What it says underneath oxygen is 15.99. And again, I decided to round it to 2 after the decimal here so I don't have to write so many numbers. And so I called it 16.00, which is what happens if I round this 99 up. I get 16. Okay. So we got our 1 mole of calcium at 40.08 grams per mole. Our 2 moles of chlorine, 1 times 2 times 1, that's 2, at 35.45 grams per mole. And our 4 moles of oxygen, 1 times 2 times 2. So 1 times 2 times 2. That's 4 moles of oxygen. Okay, and that gives us 64 grams. Then to get the mass of a mole of calcium chloride, which contains all of these atoms, I add all these masses together. And I get molar mass of 174.98 grams per mole. So that's if I add all these up. So what does this mean? This means that if we have 1 mole of calcium chloride, that contains 170, that is the same as saying 174.98 grams of calcium chloride. How is there 4 oxygens? That's a good question. So again, we've got 1 calcium in here. And what this means is we have 2 chlorides. So 1 ClO2 here, and then another ClO2. So that gives us 2 chlorines, and 4 oxygens, 2 and 2, 4. So right, because for this purpose, because we need to count all the atoms in here, we're going to have to do what we did when we were balancing equations to count the atoms. We can either draw it out like this, as you see, to count them, and you say 2 and 2, that's 4. Okay, 1 and 1, that's 2. And there's 2 chlorides because there's a 2 out here outside the brackets. What we're trying to do is count up all the atoms inside. So that includes 1 calcium, 2 chlorines, 4 oxygens. The shortcut way of doing that is 1 times 1 for calcium. And then for these, since they're in parentheses, you got to do 1 times 2 times 1, 2 chlorines. That's the 2 chlorines here. For oxygen, 1 times 2 times 2, 4 oxygens. And then we scale it up from 4 oxygens to 4 moles of oxygen, since we want to talk about a mole of stuff. Okay. Now that is the hard part. A lot of people get stuck on that. Remember from balancing equations right before the exam that there's our shortcut for counting atoms, as we can go this number, which is 1 in this case, because we're trying to do this for 1 mole of calcium chloride, times 2 times 1, that's the chlorines, 2. Or for oxygen, 1 times 2 times 2, that's 4. And the reason why we have to break it down atom by atom is because for the masses, they're all given atom by atom on the periodic table. So here, it's the masses are per atom. So we have to figure out what are all the atoms in there. And every single one of these atoms has the mass underneath. So that's how we figure out the molar mass of calcium chloride. And we're going to use this in a bit. But there's one thing I want to point out, and it has to do with counting atoms. So a lot of the times we want to know how many atoms are in one particular thing. And so we need to make a relationship between how many of the molecule, the formula unit we have, and how many of a particular atom are in this. That's going to serve as a conversion factor for us. So, for example, with the spider here, Oops. So for the spider here, if we have 1 spider, it's also safe to say we have 8 legs. So having 8 legs is essentially equivalent to having 1 spider. If you have 1 spider, you have 8 legs. If you have 8 legs on an insect, you have 1 spider. Or if you have a chair here, whoops, I keep doing that. If you have 4 legs, you got 1 chair. And if you got 1 chair, you'll have 4 legs. It takes 4 legs to make the 1 chair. 1 chair has the 4 legs. So these are 2 ways of talking about the same thing. Now, obviously, these legs are not the same thing, right? But we can still make that relationship, whether it's legs or something else that we're talking about. Same is true with atoms. If you have 1 water molecule, that contains 2 atoms. So if you're talking about 2 hydrogen atoms, you might be talking about the 2 hydrogen atoms in 1 water molecule. Just like with the legs, you might be talking about the 4 legs on the chair. You might be talking about the legs on a spider. Either way, regardless of the molecule here, if you have 2 hydrogen atoms in a water molecule, you've got 2 water molecules, or you got 1 water molecule. If you've got 1 water molecule, you've got 2 hydrogen atoms. And so you can do this with any type of atoms in any molecule, just the same way we did it for legs in a chair or a spider. And making this relationship is what students tend to struggle with. Another way too is just like we scaled up for the other things, we could scale this up too. We could say, well, we could also say if we have 2 mole, we can have 2 moles of H atoms if we have 1 water molecule. Okay. So this type of relationship you also need to be able to do too. Okay. Now, for our, here's another example that has to do with molecules. So notice how for the H atoms here, if I have 2 H atoms, those are in 1 water molecule. If I have 1 water molecule, I have 2 H atoms inside, and I could scale that up to the mole. I could say what's 1 mole? I forgot the mole. That's very important. 1 mole of water molecules has 2 moles of hydrogen atoms in it. That's another relationship that's also useful. So if I have 1 CCl4 molecule, that has 4 chlorine atoms in it, these 4 green ones here. 1, 2, 3, 4. And you could say if I have 4 moles of chlorine atoms, that's equivalent to having the atoms in 1 mole of CCl4. So we can use this with the mole or not. So yes, one of these has 4 chlorine atoms. Also, 1 mole of these CCl4s has 4 moles of chlorine atoms in it. Both of these types of relationships will be useful to us. It'll be another conversion factor. Yeah. Questions there? For the lessons, I'm going to just use the slides. So I had the printouts because they were shorthand for printing something, but I felt like the real notes were the slides. So what I'll be doing is I'll be giving you the slides themselves. I would give you printouts because they were basically the same as the slides, but they were shorter. So I didn't have to print out a whole giant kill a tree basically to give you the notes. But now the notes can be the lecture slides themselves. They're better because they have pictures. I just did that to save paper when we were in class, but you'll always have the slides from me. Yes. So that will be the notes. Mm-hmm. And the notes were basically just reproductions of the slides anyway before. So these slides are up there right now. Yeah. Okay. So now let's use this information we just talked about in order to say things about how many atoms we have of calcium chloride, maybe how many oxygen or chlorine atoms there are in there. We have to keep in mind our molar mass that we determined before. The molar mass was 174.98 grams per mole, right here. So this means 1 mole of calcium chloride is 174.98 grams of calcium chloride. And so our first example question is, how many moles of oxygen atoms are there in 2.3 moles of calcium chloride? So the hard part is you have to figure out which relationship that you need to use. So here I need a relationship between moles of calcium chloride and moles of oxygen atoms. So what we're going to do is we're going to use the one where we're counting inside how many atoms. So we already figured out that 1 calcium chloride contains 4 oxygen atoms. So what we're going to use is the fact that 1 mole of the calcium chloride it's supposed to be a parentheses, whoops, ClO2. So I'm just going to type it. So we're going to use the fact that 1 mole of CaCl2O2, this one, is the same as having 4 moles of oxygen atoms. Okay. So if we have 1 calcium chloride, we have 4 oxygen atoms. If we have 1 mole of calcium chloride, we have 4 moles of oxygen atoms. And that's our relationship here between moles of oxygen atoms and moles of calcium chloride. That's what we're going to want to use. So let's write our data here. This is not data, what I just wrote. It is a conversion factor. How can I tell that this is a conversion factor? It has a what in it? Equals, right? So we don't want to start with that. Instead, we want to start with our data like this, 2.3 moles of calcium chloride. Okay, so this is number and unit. So we start with that, 2.3 moles calcium chloride. Now we want to use our conversion factor to convert between moles of calcium chloride and how many moles of oxygen atoms that is. Okay, but first of all, we know what we're going to put on the bottom here has to be something that will cancel with this. So it has to be the same unit as what's here. That's always true. So we put that mole. Yeah, it has to be mole, exactly. Yeah, right here, mole. So we put the mole. And so we put this side of the conversion factor. It has the number 1 next to it, and it has moles of calcium chloride. The result is that these can cancel. That's what we're looking for. Now what we want to put on the other side of the conversion factor is this side that we made. We saw that 1 calcium chloride has 4 oxygen atoms in it, or scaled up, 1 mole of calcium chloride has 4 moles of oxygen atoms in it. So we're going to put this on the other side. Whoops, it's holding control. And so that's that there. And now that gets us the answer that we wanted, 4 moles of oxygen atoms. Was this in the way? Sorry if that was in the way. I think it should be hiding those boxes. Let me know if anything's bad, like sound goes bad or something's blocking so you can't see it. So yeah, so we put that in our calculator now. So let's go to the calculator. I think I still have it open. The calculator says we're going to do 2.3 times 4, and that is 9.2 moles of oxygen atoms. I should put this over here so I can keep this full screen. Okay, so that's the first example. Now the next one is going to ask us, no. Maybe I can get it to go. Okay, here we go. All right. Okay, so the next problem is going to ask us, what is the mass of 8.22 times 10 to the 22nd formula units of calcium chloride? All right, well, now we're starting with how many of these. Okay, and we want to get to mass. So this is actually going to take a couple steps, so we should probably make a plan. So our plan is going to be that we want to go from the number, so how many calcium chlorides, so which I'll write as CCALO2 how many of them, to, and this is going to be the rule of the game here, is that generally what you're going to want to do is go for the mole. Now, there used to be this really old guy at UCR. He was like 90 years old. He'd teach chemistry, intro chemistry, and he'd say, go for the mole all the time. And That's what you want to be doing. You want to go for the moles. We want to go from how many of these to how many moles, because that's our chemist way of counting things. And you're going to find that going for the mole is often what you want to do. So we go for the mole, and then we are going to have a way of turning the moles to grams. Does anyone remember the relationship? What relationship we need to go between moles and grams? What is the relationship we need to go between moles and grams? The molar mass, which we've got. So we're going to here use the definition of a mole. So mole is 6.02 times 10 to the 23 things to get from how many to how many moles. Then we're going to use the molar mass to go from how many moles to how many grams. So let's start this. We're going to start with our data, which is just number and unit. This many, yep, 6.02 times 10 to the 23, that's it. That many formula, so we have that many formula units, which remember formula units is the word like molecule, except for ionic compounds. So 8.2 times 10 to the 22 calcium chloride. I didn't write the word formula units, I just wrote the formula. This is just to keep it shorter, so it's not so long. And now we have to calculate, or we have to cancel our number of calcium chlorides. So what we're going to be using here is our 6.02 times 10 to the 23. We just have to decide where to put it. What we want is the number of calcium chlorides that is equal to a mole of them. And that number, what mole means, so mole here means a number. It means the number 6.02 times 10 to the 23. Now notice I didn't use the second 2. This is because my original data only has 2 sig figs. So if I write this with 3 sig figs, it's totally okay. Of course, if you use the extra 2, that's totally cool too. Just make sure when you're using your conversion factors, just make sure they have at least as many sig figs as the data that you started with. So this is going to cancel for me my calcium chlorides. So you can see they cancel right there. That's how many of them. Now we've got how many moles of them. And that's what we can use now. This we can use this molar mass up here for. What this means is that 1 mole of this equals 174.98 grams. So that's where we're going to go next. All right, so let's do that. So we're going to set up another conversion factor. We want to go from moles of calcium chloride to grams. So moles will cancel. So we need always the same thing. We always know the unit here, the unit down here has to be the same as the unit up here so that they can cancel, right? That's the whole name of the game. We just got to figure out what goes here and what else goes here. Well, with our molar mass, the number that we want a relationship here between how many moles and how many grams. That's the molar mass. So when you calculate the molar mass, it's always 1 mole of this. And how many grams? Oh my gosh, I copied it wrong. Let me fix that. So how many grams is not 164, it's 174. I pressed it wrong. And so I'm going to change this to 174. Why can't I select it right now? Oh. 174.98 grams. Okay. Okay. And so now the number that goes with grams is 174.98. And that is the mass of 1 mole of these. So now we have to get out our calculator. So let's go to our calculator. And remember, in our calculator, we never press times 10 to the power of something. We use our EE or our EXP button. So it's going to be, we'll start with what we have on the left here, 8.2 times 10 to the 22. So 8.2 EE or EXP on my calculator, 22. And then for every number that's on top, we'll press times. And for every number that's in the bottom, we'll press divide. We don't have to put the ones. So we can press divide and put what's called Avogadro's number, or 6.02 times 10 to the 23. Divide by 6.02 EE23 equals. And so that's how many moles of calcium chloride we have, 0.13 moles. Next, we want to multiply that by our number up top. So times 174.98. And that gets us 23.83. I don't know if that's too small there. Oh, wow, we get a little extra window here. So that gets us this 23.83. So going back to our slide here, I wrote 23.8 out of my calculator. Now, is that what I'm going to write for an answer, though? What am I not thinking about here? There's something really important to do at the end. What is it? Hopefully, you guys remember from the beginning. It's been a while. Sig figs, okay? Remember, when we're multiplying, we count the sig figs. This number, 8.2, has 2 sig figs. This one, we wrote it with 3 sig figs. We could have written it with more. This one, we wrote it with 5 sig figs. We could have gotten more from the periodic table, but our limit should always be our data, 2 sig figs. So we have to round this to the second place where the 3 is. So our answer should be written as 24 grams of calcium chloride. All right. So questions on that example there? So in general, the way that we get between all of these things, volume of gas is what we're going to come back to pretty soon. But if we want to go between a number of things and how many moles of that it is, we use Avogadro's number. 6.02 times 10 to the 23 is 1 mole of something. Particles could be anything. Atoms, molecules. Oh no, the last two were connected because they were both having to do with calcium chloride, but they were also different because I asked different things in them. So for the first one, I asked, if you have 2.3 moles of calcium chloride, how many moles of oxygen atoms do you have? Oh, the calculator's blocking, thanks. So I asked, if you have 2.3 moles of calcium chloride, how many oxygen atoms do you have? Okay. And then for this one, I was asking you, if you start with this many things, how many grams will that be? So for that second question, what I started with was how many things, the number of particles. And our first step was to go from the number of the formula units to the moles. For that, we use the Avogadro's number. Then the second part was to go from the moles of that to how many grams. For that, we used the molar mass, which we got using the periodic table. Now, what you must also be able to do is within a substance, figure out how many particles are in there. And that's what we did in the first problem. We counted up, oh, if I have 1 of these calcium chlorides, I have 4 oxygens. Or if I have 1 mole, I have 4 moles of oxygen. That gets you from how many in a compound to how many atoms are actually in there. And so there's lots of different types of ways these calculations can go. As you can see, I asked several different types of questions already. That's what experiment 3 is going to be mostly about, is practicing to make sure that you know which conversion you're trying to do. And so, yeah, And that's going to be experiment 3. So before I go on to the rest of the lecture, why don't I talk a little bit about experiment 3 to give you a few more examples of this type of question. So I'm going to now open experiment 3. You can find experiment 3 in Canvas. It's there and available. So again, if you want to get to experiment 3 and download it, it is in our unit 3 here. There's the document. You can download that. So you just click that there, click to download it here. Okay, save it wherever, and then open it. Okay. So there's our experiment 3. And so what you're going to see on experiment 3, so this is the online version, but I took pictures. I had already had pictures of experiment 3 because I was kind of planning to put them in there anyway. We have various stations. So it says, part A says visit stations 1 through 6 here, and observe samples of elements and compounds. So these are the pictures of those samples of elements or compounds. So we have 123.6 grams of lead, and we have 216.3 grams of lead here, and 112.9 grams of lead at station 3. Okay. And so what I'll do is I'll look at the number of grams. So this is to give you a picture of you know, what 123.6 grams of lead looks like. I'd like to do station 2 real quick, just to point something out. So what I do essentially is I'd copy these masses in. So I have 123.6 grams for station 1. And so the substance name is lead. So you can either type this in there or you can write it in, either one. And the mass is 123.6. 123.6. And if you print this out, you can just write it in and then take a picture and send it to me. That's fine. For station 2, it's 216.3 grams of lead. So the substance name is still lead. But the mass now is 216.3 grams. 216.3. And then I'll just write the third one, station 3, lead 112.9. Well, you get the idea actually. So what I'm going to do is I'm going to show you an example with the first of these, the first 2 of these, and I'll show you in this example how to actually type up stuff in formulas and as conversion factors if you actually want to type it up instead of writing it in. You will need Microsoft Word for this. You probably could do it in other programs, but remember Microsoft Word is free for students. And so you can see I'm doing this all in Word. Again, if you need to get Word, if we go back to the home, there's a link right here, free student access to Microsoft products. If you click that and put in your student email and log in, you should be able to get the free access to the Microsoft products. Alternately, you could open these in Google Docs. That's another possibility, and edit it there. So yeah, so Google Docs is another option. Google Docs. So go to Google Docs. So I go to Google Docs and I go to like my drive here, and I could open, this was your exam, I could open this in Google Docs. Oops. And edit it anyway. You can edit a Word document in Google Docs. That's the other option. But I highly recommend that you get Word if you want to type things in this way. And it's free through the campus. So we were asked to convert these grams of lead to moles and to how many atoms. Okay. So how to get between grams and moles, what information do we need? And where can we get it? There's somewhere to periodic table. Yes, 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 indeed. And of course, you guys are always free to talk if you want to, but you don't have to. But yeah, we got to go to the periodic table and figure out how many grams is a mole of lead. So we go to the periodic table here. Oh, okay. Lead, 207.2 grams per mole. Okay. So what this is telling us is, I can write it here to remind myself, 1 mole of lead, Pb, is 207.2 grams of lead. Okay. So that's my relationship there. And I'm going to use that as a conversion factor. So this is how you can type in conversion factors now into Word. You can either write this here and take a picture, or you can type it in. I'm going to show you how to type in things in now if you want to do that for your reports. You go to Insert, and then you choose Equation. And here you can begin to type an equation. Now I'm going to start by writing down my data. 123.6 grams of lead. Okay. And then I'm going to have to multiply by a conversion factor. So I'm going to go up here into this bar. There's lots of symbols up in here you can use. I'm going to use the times symbol. And then in terms of fancy math and equations, there's all these here. So I'm going to put my conversion factor in a bracket. I'll choose this one here, and it makes a bracket. So I like to put the bracket first, and inside the bracket, my conversion factor is going to be a fraction. So I'll click the fraction here and put in a fraction like this. Then I just have to decide what goes on the bottom and what goes on the top. What unit am I sure has to go down there on the bottom? Grams of lead, right? It has to, because we have to cancel it. So that's going to be our unit. Now we just need to know which number goes with that unit. Well, in my conversion factor between moles and grams here, I have how many grams is 1 mole. So on the bottom, what goes with that is 207.2 grams lead. And that will result in a canceling between these. So this one here will cancel with this one here. And then the other side will be the other side of my conversion factor, which is, this is 1 mole of lead. Okay. Then we get our calculator. All right, and we do 123.6, and then this is on the bottom. So we're going to press divide, 207.2. And we get 0. So our calculator gives us this big long number, but remember, I want to round to 4 sig figs because my 123.6 had 4 sig figs. Okay. So I would write my number as 0.5965, and I won't round the 5 up because this is a 2. So I say 0.5965 moles of lead to be specific. I can type this in here, PB, if I'm being very specific. Now notice that a mole of lead is 207.2 grams of lead. Okay, look at this one. This one's about a mole. So if you wanted to know what a mole looks like I said, a mole is about a handful. So these jars represent, this is a half a mole about, a little bit more. This is a little more than a mole. Okay. I did choose the right number, right? Yeah. Okay. So yeah. So these are, about a mole's worth. And So you'll continue to do these types of conversions. A lot of people, so the next few stations here are these ones. A lot of people get hung up on station 6. So I'll say something about station 6. So if we look at station 6, it has what we call here, or what's said here is 2.45 times 10 to the 23rd tin atoms on the picture there. So I will write that in on station 6. My substance is tin, which is SN, capital S. Okay. And our atoms is 2.45 times 10 to the 23. So I'm going to give you another little tip here. 2.45 times 10 to the 23. So I write 23, and now I want to make this an exponent, right? The way you can make this an exponent is there's a button up here. That's the superscript. That will make it look like an exponent. The other way you can do that, there are shortcuts. So if you want to do a superscript, you can, or if I want to make this a subscript, I can press Control plus. So this is Control plus, Control plus. So I'm holding Control and I'm pressing plus, 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 plus. When you press plus, it does the subscript. If you hold Control and Shift and press plus, it will do a superscript. So now I'm holding Control and Shift and I'm pressing plus, 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 plus. So when you see me typing things really fast, that's how I'm able to do it. I'm not actually going over there and hitting these, but you can always hit those. And actually, it wasn't that many moles. It was that many atoms. Let me see. Seems to be a problem there. Station 6. Oh, because I copied it in the wrong part. Let's take that out. Control X. We're going to put this here. This many atoms, not moles. If you had that many moles of tin, it would be bigger than the size of the Earth. I don't know why when I copy this, it's not copy. Okay, paste. There we go. All right, so we now have how many atoms. And so we can convert these to moles. Let's do that as an example problem. So again, if I want to type into this, I go Insert, and I go Equation, and then I have a box for equation. And I type 2.45, and I can either press X or I can use the times. Times kind of looks nicer in the equation, times 10. And now I want to do an exponent. So doing an exponent can be tricky in the formulas. It's easy if you're doing it in Word, but if you want to do a superscript here, an exponent, you have to click this one, script at the top, and then choose this. And what you see here is that it made a box for what's not in that superscript and what is. So I might want to take this 10 and drag it in there. So now this is what's being next to the superscript. And my superscript is going to be 23. Then if I want to get out of superscript, I can hit the right arrow. That will also work on your mastering chemistry as well. The right arrow gets me out of the superscript, or I can just click out of it. So if I click over to the side here, I'll get out. And then I want to do a conversion factor. So I'm going to use the times button again. I'm multiplying by a conversion factor. So I put it on my brackets like that. And inside my brackets, I put a fraction. Okay. And then I'm going to put my conversion factor. So this is 2.45 times 10 to the 23 tin atoms, which I'll show as SN. Tin. Whoops, sorry, it's blocking again. So yeah. And so that's my 10. And I'll show you how to do the exponents again too, in case you didn't see because of the calculator. So now I want to apply a conversion factor. I'm going to try to go from, so what I'm going to cancel here is tin atoms. Now I can write atoms here too. You don't have to. We are talking about atoms. I'll put it in parentheses because you don't have to write atoms here. And I usually don't. I'll just write tin. You don't have to write that, but you can. All right. And we want to go to moles of tin atoms. So I could even write in my tin if I want here too. Tin, moles of tin. Okay. And again, I can write atoms afterwards. I don't have to. I want moles of tin. So moles of tin. So what's my relationship between how many is a mole? How many is a mole? So if I say 1 mole of tin atoms, how many is that? It would be 6.02 to 3 sig figs. Yes, yes, 6.02 times. So I can go back into the equation here. There will be this equation. As long as you're typing an equation, there'll be this equation tab you can go back to. Times 10 to the 23rd. And again, I'm going to want to do the subscript. So the way I do that is for the 10, the easy way is to highlight the 10 and then go to script and then choose this one with a superscript. And then I put 23. Okay. Now, usually I don't put the word atoms too. If I write the symbol for an atom, I think it's an atom. If I write the symbol for a molecule, I think it's a molecule. If I write a symbol for an ionic compound, I think it's the formula unit of that ionic compound. So I'm just going to erase the word atoms. I don't really need it. I know when I write SN, I'm talking about tin atoms, okay? So what's key here is that the word mole means this number, okay? That's why this conversion factor works. Mole and this are the same thing, exactly. Why is it 6.02? That's a great question. The technical answer for that is there are ways of figuring out how many atoms. You can't do it by counting. You can use machines and do estimations. And what scientists figured out by using machines is if you have 12 grams of carbon-12, only carbon-12 atoms, those that have 6 protons plus 6 neutrons, the number of atoms in 12 grams of carbon-12 is 6.02222 times, or 22, and it goes on and on. We can see more of those if you want here. Mole. Oops. 1 mole equals, if we go to Wikipedia. So if you look here, a mole is actually 6.0221476 if we use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sig figs. So I only showed it to here, but there are more sig figs. This is the number of atoms that are in a sample of 12 grams of carbon-12. And then all the other stuff on the periodic table is kind of based around that. So that's where the number for mole comes from. But that's a very good question. A lot of people don't ask that question. They just go on and start to use this number. But that is where the number comes from. They used a fancy way to count how many atoms are in 12 grams of carbon-12, and they called that the mole. And then scientists went to work figuring out what is the mass of a mole of any other atom, you know. Okay. So did that answer your question? So notice now we're going to cancel tin atoms. Oh, okay, great. Yeah, that is, I don't always teach that in Chem 101. I always teach that in general chemistry, but yeah, that's where the number comes from, the fancy science behind it. And so that gives us moles of tin atoms. That's exactly what we were looking for. All right, moles of tin. That's what we wanted. So again, let's do one more example with the calculator. Make sure to use your EEs. Don't type out times 10 to the power or whatever. Don't do that. Okay. So we're going to now clear our calculator out, and we're going to do 2.45 times 10 to the 23. And we're going to divide by, oh, and I went really fast with my EE because I'm so used to it. 2.45, and we don't type times 10 to the power, right? 2.45. We don't type times 10 to the power. You use our EE or our EXP button, 23rd power. When we press equals and look what this number means, it's really, really huge. And then we're going to divide that by Avogadro's number, the 6.02, to EE 23. And we get that our moles of tin is 0.4069, so forth. But we're going to stop at 3 sig figs. Remember, front zeros are never significant. It's going to be the 4, the 0, and the 6. And since the 9 is next to the 6, we're going to round this up. So we'll say 0.407. Like that. Yep, 0.407. And that's how you'll answer these. So in station 7, you're going to start with grams. Okay, you're going to have, in station 7, you're going to have 2 compounds. You're going to start with grams, and you're going to get to atoms, okay, the number of particles. So I'm not going to do this one for you. I think that it's, well, maybe I'll do the first one. I'll leave the second one to you. So we have 40 grams of sulfur. Unfortunately, this is only written with 1 sig fig. I don't like that that's true, but I'm going to call it 40 point so that it will have 2 sig figs, grams of sulfur. Well, a gram is already there. So our A is actually sulfur, S. Okay, and what we're asked is to get to how many moles that is. Okay, so we're going to need first, going back to the slides here, we're going to have to first go for the mole to find out how many of those atoms there are, because we're given the mass here. We're going to need to go to the number of moles. So going between mass and moles requires the molar mass, which we get from the periodic table. And then we're going to have to go from moles to the number of atoms, particles, atoms in this case. Okay. And how are we doing on time? We've almost done an hour, so I might take a short break and then we'll finish the lecture after, just in about 5-10 minutes. So next, we're going to copy down our 40 grams of sulfur. So I'm going to put a new equation in, insert equation right here. Type 40 point to give it 2 sig figs, grams of sulfur. If you end up doing this with 1 sig fig, I understand. That's the way it's written on the bottle. Unfortunately, there's no point behind it. There should be, I feel like, but okay. And then we're going to do times, and we're going to put in a conversion factor. And our conversion factor is going to be to go for the mole. We want to go from grams to moles. How do we go between grams and moles? Where do we get that conversion factor for going between grams and moles? What tells us how many grams are in a mole? The periodic table, right? So this is sulfur. So this number here, again, 32.06, this tells us 1 mole of sulfur atoms is 32.06 grams of sulfur. So that's what I'm going, I'll use that relationship. So we know what unit has to go on the bottom. It has to match this one's. So it's going to be grams of sulfur atoms. And the number that goes with grams is this right here, 32.06, 32.06 grams of sulfur. And that is equal to, what this tells us is that this many grams of sulfur is equal to 1 mole of sulfur atoms. That's how much they weigh. Notice here our grams of sulfur are going to cancel. So I'm just going to use a strike through here. Grams of sulfur cancels with grams of sulfur. And now we have moles of sulfur. But that's not what we're asked for. We're asked for how many atoms of A is sulfur. How many atoms of sulfur? So that's where we need the relationship between how, we need the number that tells us how many a mole is. So going back to equation here on this tab, I'm going to do times. Okay. And then I'm going to put in a parentheses and do another conversion factor, because we're not where we want to be yet. Now I know every time before I even turn my brain on, I know what the unit's going to be. The same one is right here. I could basically copy this. What's on top? What's on top has got to be on the bottom. And I want to go from moles to how many? Well, 1 mole of sulfur or anything is 6.02 times 10. I'm going to highlight the 10 and put a superscript on it up here to the 23rd. Now I'm going to press the right arrow, or I can click out, or I can press the right arrow. I want to be on top though, so I might just press the right arrow. So I pressed right on my keyboard, and I was able to now put space sulfur. And of course you can write atoms, okay, if you want to. You don't have to. If I write the symbol for just an element like this, I'm talking about the atoms in that element. And notice here that the moles sulfur is going to cancel with the moles of sulfur. And our unit at the end we get is the number of sulfur atoms, which is what we wanted. Now we put this in our calculator. Okay, and remember, everything on the top, press times before you enter it, and everything on the bottom, press divide before you enter it. Okay, bring up the calculator here. All right, so we're going to put 40. We're going to press divide, and then we're going to put 32.06. Then we're going to press times, since this number is on top, times. And we're going to put 6.02, and remember to use your EE. Don't press times 10 to the power. Press EE or EXP, 23. And of course, this will be a big number. If you end up using the Windows calculator a lot, this button will turn it from regular notation back to scientific. So I'm going to pull the first 2 sig figs, the 7 and the 5. Since this is a 1, I will leave the 5 alone. So I'm going to say 7.5 times 10 to the power of 23. And I can select that and press Control Shift plus, or I can press this button up here. And I think my stuff went to the next line. Let me make sure to fix that. Oh. Doesn't look so great. Yeah, well, it works. So that's how we do that kind of problem. Anyone want to ask a question on that? Is it only one sig fig? I put 2 sig figs. And the reason is because, yeah, on the label here, let me get rid of the calculator. On the label, actually, it's only written with 1 sig fig. There isn't even a point. I encourage you guys just to have at least at least a couple sig figs to write this as 40 point. So I wrote it as 40 points so that the 0 would be significant. So this one, I think you should write it as 200 point. So it will have 3 sig figs. But if you do your calculation and write it with only 1 sig fig, that's fine. Here I used 3 sig figs because that was plenty to cover my 2 here. I could have used 6.022 as well. Remember, going back to Wikipedia, there are lots more sig figs known for this, right? We know sig figs all the way up to, way past the decimal. But I never have you use more than the first 4 here, 6.022. You'll use as many as you need. Other questions? There's one more section I want to prepare you for. Oh, this one asks, okay, just to tell you how to do this when you go to do it. For station 8, it will say how many atoms in the sample, okay? What this next question is talking about is it's saying if you had the same number of atoms, but they were not atoms, or they were not magnesium, they were instead tin, what would they weigh? Yeah, what would the mass be? So this is station 8 is all one question. When you figure out how many atoms you have here, what you're going to do is copy that number of atoms and you're going to put it down here, and then you're going to figure out, well, how many grams would those atoms weigh if they were tin? So that's how you do station 8. With station 9, we have 19.0 grams of iodine. So if we look closely at the picture there, it's 19.0 grams of iodine. Okay. So we're going to put that here. So we have 19.0 grams of iodine. And what's important is this is I2. So if you want to go between grams and moles of I2, you need to get the molar mass for I2. Okay. So if we have I2, so 1 mole of I2, and this is where people have a hard time, is they don't count, they have a hard time. It's really tough at first to get the idea of counting the atoms that are in the molecule. Iodine is an element that comes in the form of a molecule. So if I have 1 mole of I2 molecules, that means I have 2 moles of I atoms. Okay. Or equivalently, we could say, if we just want to work with 1 I2 molecule, if we have 1 I2 molecule, which I'm writing in parentheses, the word molecule, I wouldn't necessarily have to write that. If I have 1 I2 molecule, that is equal to having 2 iodine atoms. So if I'm looking at an I2 molecule, it has 2 iodine atoms stuck together, right? So 1 iodine molecule has 2 iodine atoms. We can always scale that up to a mole. So 1 mole of I2 has 2 moles of I atoms. And we may need to use either of these. It's when people start having to decide which one, I think, that they have a really hard time. Now, the way I like to write this too is without the atoms and molecules. So I'll say, if I write I2, well, I know that's a molecule. I don't really have to say that. If I write the symbol I know I'm talking about the atom iodine and not the molecule. There are a number of elements that are diatomics like this, but this works for any molecule. So if I want to calculate the number of moles of iodine molecules, what I need is the molar mass of iodine. So 1 mole of 1 mole of I2 is 2 moles of I atoms. So if I want the mass of that, well, I have 2 moles of I atoms. Insert equation. So 2 moles of I atoms, but according to the periodic table, 1 mole of iodine atoms. Okay, I'm going to take off the word atoms because we're talking about iodine atoms here. Okay, I can just indicate it with I. If I go to my periodic table, that weighs 126.9. And important there is that's the mass of a mole of iodine atoms, not a mole of I2 molecules. If you want the mass of a mole of I2 molecules, well, you've got to calculate the molar mass for that, just like you would for anything else. So it's the same as we did before, except it's only one type of atom instead of multiple types. 1 mole of I2 is 126.9 grams of iodine atoms. Okay, 129.6 grams. I just say grams. That's the mass. Okay, so that means the molar mass of iodine is 2 times this. So we'd get our calculator again. Go get your calculator. 2 times 126.9 equals. So it's, whoops. My calculator. Come on, come back, calculator. Okay. I might want this in normal notation. 253.8 grams per mole. 253.8 grams per mole. Or in other words, what we're saying is 1 mole of I2. So one mole of I atoms is 126.9 grams of I atoms. But 1 mole of I2 so 1 mole of I2 molecules is 253.8 grams of I2. See the difference there? So this is the molecule. This is the individual atom right here. Okay. But notice in either case, what's here is a 1. That's really important. A lot of times people will say, oh, there's a 2 here. I should put a 2 here. No, 1 mole of I2 molecules has 2 moles of I atoms in it. So it weighs 253.8 grams. 1 mole of iodine atoms weighs 126.9 grams. That's why a mole of I2 weighs twice that, because it has in it 2 moles of I atoms. So the conversion factors you're going to be using in this part will be these, both or either of these, and this one right here. And if you guys get stuck, let me know. I'm going to have you start to work on them over the course of the week. When we get back to lecture, I'll answer any questions that you guys have about this one. And you should complete this to the end and upload it as soon as you can, as soon as you feel confident in your answers, and I will grade it. Of course, I put the due date quite far away, but you should do it sooner rather than later. So at this point, because I spent a lot of time on syllabus today, but I still want to do lecture, I am going to finish off the lecture. But before we do that, let's take a 5-minute break. Okay, so I'm going to write here on the screen, BRB 5 minutes. So that's going to be at, let's make it 7 minutes. Okay, until 2:30. So I'll be BRB at 2:30. And we'll continue and finish the lecture. Usually things won't be this long, but for this time, we really need the time to get started, I'd say. So BRB at 2:30. And we'll finish the lecture. I'm gonna get a drink of water, but I'll still be here. But go ahead and take a break if you need it, get some food or whatever. I stream StarCraft, so I'm really trying to catch up on my teaching stuff, but I've been really wanting to play StarCraft too. If you guys want to check out my Twitch channel, now I do sometimes drink beer or something on there, so don't judge me. But you can, well, I'll just type it in the chat actually, rather than advertising it. So this is the way, actually I have a much bigger setup. Usually I have just a little tiny green screen, but I knew for if I wanted to give lectures, I was going to need a big one. Have no fear of ice cold beer. Yeah. I knew that I was going to need a much bigger setup. So my whole living room is basically a giant green screen right now. But that makes things easy for if I get a chance to play games. So if you guys want to see me playing games, although you should be studying your chemistry, but I mean, I watch Twitch at night when I'm relaxing, so. I didn't answer your question. I stream StarCraft. It's my favorite game. It's the only game I mean, I play lots of games in the past, but I'm really stuck on StarCraft. I have been for a long time. It's the new chess, if you ask me. It's a strategy game. All right, so I'm back. Hopefully you've gotten your snack or your drink. We're eating in lab. Oh my God. Okay, anyway. Uh, so I'm going to move on here. So again, the mole here is the center of everything. So that's the way we count things. And if you're uncertain, go for the mole. And again, with the number of particles, we can look further within the molecule or the formula unit and see how many atoms are in there. So those are the kinds of problems that students get stuck with sometimes, and so that's why I wanted to demonstrate a few of those, at least demonstrate a little bit of that on the lab assignment. Okay. So another thing that we can do, given certain information, is find what percentage of a substance by mass is a particular type of atom. What percentage of the stuff is one element, like oxygen, and what percentage by mass of the stuff is another element. So percent mass is the mass of the atoms of a particular element over the mass of the whole compound. For example, let's say we burn some metal. This is something that they did a lot back in the old days when they were first trying to figure out what the elements even were. Their solution was just burn everything and see what happens, okay? So if you burn chromium or some metal, but chromium in this case, it reacts with oxygen. So something that chemists noticed a long time ago is that, oh, we burn this thing and then what we get at the end has more mass. And it has the mass because that metal attached to oxygen atoms to make an ionic compound, a metal oxide of some kind, in this case, chromium oxide. So then they would figure out, well, what percentage of the mass is the chromium, and then what percentage is the other stuff that it picked up, which, as we know now, is the oxygen. So to figure out the percent of anything, remember, percent in general is just the part of something divided by the whole thing, then times 100% to make it a percent. So the part here that is the chromium is this. It's the 3.58 grams. That's the part that's the chromium right here. Then the whole thing, the chromium and the metal, or the chromium and the oxygen rather, the metal oxide is this. So to find the mass percent of chromium, we would take the mass of the chromium, which is the 0.358 grams, and we divide by the mass of the metal oxide, or the chromium oxide in this case, which is the 0.523 grams. That will give us a fraction. And then if you ever want to turn a fraction into a percentage, you just multiply by 100%. Remember, 100% means 100 per 100, so you can always multiply it by it. Notice here that our gram units are going to cancel. So the gram units cancel, but we keep our unit of percent here. Okay, so we have percent. We get 65.85% here. And so in this metal oxide, 68.5% of the mass is chromium atoms, and the rest, which is 31.5%, would be oxygen. And so that's one way in which chemists started to analyze, well, what are these compounds that are being made if we burn some metal, for example, they burn all kinds of metals or burn other things and say, oh, the mass increased by a certain amount and it's different for all of them. Well, we can use that to analyze what these elements are by what percentage they are of a particular element. We can analyze each compound based on what percentage of a particular element it is. For example, this chromium oxide is 68.5% chromium. Now, the reason for doing this is this gives us another type of conversion factor we can use. This conversion factor will convert us between grams of a particular element in a compound and grams of the entire compound. So here's another example. If we have sodium chloride, which is table salt, By mass, it is 39% sodium atoms, and the other 61% are chlorine atoms. So let's say we want to know how much sodium we get in our diet by eating a certain amount of sodium chloride, because that's the part we're concerned about with, right? The RDA for sodium is we can only have so many milligrams of sodium per day. But the way we usually eat sodium is often in the form of sodium chloride. So if the percentage of sodium in sodium chloride is 39%, what that means there is that if we have 39 grams, or if we have 100 grams rather of sodium chloride here, we also have 39 grams of sodium that are in those 100 grams of sodium chloride. So remember, percent means per 100. We have 39 grams of sodium per 100 grams of sodium chloride. And remember that per. When you hear per or equals, you should be thinking conversion factor. That's what I'm going to use this for. So let's carry this forward to the next slide and see what happens if we are asked a problem about this. So again, writing this as a conversion factor, this is a conversion factor. We can write it, any conversion factor, in two ways. We can put the 39 grams of sodium on the top and the 100 grams of sodium chloride on the bottom, or we can do the opposite. We can put the 100 grams of sodium chloride on the top, and we can put the 39 grams of sodium on the bottom. The way we decide is always going to be based on what units we want to cancel. But the relationship is 39 grams of sodium is equal to 100 grams of sodium chloride, or in the fact that for 100 grams of sodium chloride, there are 39 grams of sodium in it. Anyone have a question at this point about the mass percent? Okay. So here's a kind of problem that would be related to that. So we already figured out that we can use this relationship, 39 grams of sodium per 100 grams of sodium chloride. So it says the FDA recommends that adults consume less than 2.4 grams of sodium per day. How many grams of sodium chloride can you consume to be in the guidelines, still be in the guidelines? So we know how much sodium we can have, but not how much sodium chloride. We do recall from the last slide, sodium chloride is 39% sodium by mass. What we want to do is go from grams of sodium to grams of sodium chloride. We're given that we can consume 2.4 grams of sodium. This is what we're going to want to do. I think my animations were kind of off a little bit here. But the way that we're going to do this is we're going to write down our data. Our data is 2.4 grams of sodium. We know that's our data because it has no equals and it has no pers in it. It's just number unit. Our conversion factor is going to be this one right here, but we need to know, for grams sodium, do we want it on the bottom or the top? Well, we want it on the bottom. If it's on the bottom, the grams of sodium will cancel with these grams of sodium, and in the end we'll get grams of sodium chloride. So the grams of sodium cancel here, and we get grams of sodium chloride. Now in our calculator, what we're going to want to do is punch this in. So going back to our handy dandy calculator here, we're going to do 2.4, and then that's going to be times 100, since it's on the top, divide by 39. And that gives us 6.153 and so forth. Because the 2.4 only has 2 sig figs, we want to pick this only to 2 sig figs. So we're going to round the 1 up to a 2. And so we say 6.2 grams of sodium chloride. Questions on that example? Did I lose anybody on a part of that? Okay. Now, what if we don't have an experiment to go by? So let's say, for example, we have this molecule CCl2F2, and we want to know, and we're just given this formula, we want to know, well, what percentage by mass is this of chlorine? So first you want to assume 1 mole of the compound. This will make your calculations easier. Now, if we look at 1 mole of CCl2F2, this is the molecule here, the big green atoms represent the chlorine. There are 2 chlorines in that. You can see there are 2 right here. So if we have 1 mole of CCl2F2, it has 2 moles of chlorine atoms in it. So again, to find the mass percent of anything, we put the part that is that thing divided by the whole thing. So the part that is the chlorine is going to be the 2 moles of chlorine atoms. So we take the molar mass of chlorine atoms and we multiply them by 2 to get our mass of 2 moles of chlorine atoms. Then we would divide that by the whole molar mass of CCl2F2. So it's always the part. Here the part is the chlorine divided by the whole thing. And the key here is to assume 1 mole of the compound. That way we can just use the molar masses. If we have 1 mole of the compound, that has 2 moles of chlorine in it. So we just get the mass of those 2 moles of chlorine. It's fairly easy if we have a periodic table. And then we get the mass of 1 mole of the whole thing. We just calculate the molar mass. Okay. So let's look at this with a real example here. So here's another one with Freon 114. So this is a refrigerant. It's one of these chlorofluorocarbons that was making a hole in the ozone layer. So we stopped using Freon of this kind at some point in the 90s or something. So this is a similar compound, but it has 4 moles of chlorine per mole of the molecule. So if we want to find the percent that is chlorine, we use the chemical formula. We look at, well, if we have 1 mole of this, or if we have 1 of these, we have 4 chlorine atoms. So if we have a mole of this, because we're going to assume a mole, then we have 4 moles of chlorine atoms. So to get the percentage of chlorine, we take the 4 moles of the chlorine atoms and we divide by the mass of the whole thing, the 1 mole of the whole thing. Okay. So I haven't gotten any feedback. Everything okay on your end? Everyone's still there? Yeah. Yeah, okay, cool. All right. Just making sure. Sometimes a technical glitch happens. All right, cool. And I don't realize it. I just want to make sure you guys are good. All right, thank you. So in general, the mass percent of some element X is going to be the mass of that element in the compound, however many moles of that there are, find what that weighs, divided by the mass of the 1 mole of the compound. Because again, to make things simple, we're assuming 1 mole of the entire compound. So we get the mass of those atoms of the particular element X that are in it, divided by the mass of 1 mole of the whole compound. So here, if we want to know the molar mass of chlorine, we'll go to the periodic table and notice again that C2CCl4F2, Freon here, has 4 moles of chlorine atoms in every 1 mole of the molecule. So to get the mole mass of all the chlorine atoms, we have to take the molar mass of chlorine atoms and multiply that by 4, since we have 4 moles of the chlorine atoms. So if we go back to the periodic table, the molar mass of chlorine is 35.45. I'm going to put the slide on the side here. Okay. No. Okay. So we want 4 times that. So 4 times 35.45. That gives us 141.8 grams. And then we need to divide by the molar mass of C2Cl4F2. Okay, so let's do this kind of quick style in the calculator since we've done a few of those already. So for carbon, the mass is 12.011, and we're going to have 2 moles of carbon atoms in it. So we say 2 times 12.01. So this is going to be the mass of the carbon atoms. Then we're going to add the chlorine atoms, which was 4 times 35.45 times 35.45. Oh, and we got 165.82. Last, we have to add the 2 moles of fluorine atoms. 2 times 18.998. Oh, I think I lost my other ones. Let's get this. All right, I wanted to add 2 times, there we go. For fluorine, it was 18.998. 203.816 or 203.8 with 4 sig figs here. Then we divide 141.8. Whoops. 141.8 on the top, divide by 203.8. So again, don't have to memorize this hardcore. Just remember it's the part over the whole. So we're assuming 1 mole. The part was the 4 moles of chlorine atoms. The whole was the whole thing. So we added up the mass of the whole thing. And for 1 mole of it, it was 203.8. And we get 0.6957. That's a decimal. If you want to make any decimal percent, you multiply times 100%. And see how I keep the percent, because the percent behaves like a unit. And my number is 69.58. Right there. And that's how you get the percentage by mass, given the formula. So again, repeating the steps. Number 1, assume 1 mole. Number 2, find the molar mass of the part that you're interested in. So here we have 2 moles of chlorine atoms, 2 times the molar mass of chlorine atoms. That's the part you're interested in, the chlorine. Finally, divide by the molar mass of the entire thing, right there. Mass of element X in 1 mole of compound, divide by mass of 1 mole of the whole compound, times 100%, to make it a percent. Now, what about if you didn't know what the formula was? So back in the old days, I told you they were just burning things and seeing how much weight they gained to see how much oxygen they picked up, right? And that told them something about the compound, how much oxygen it had in it relative to whatever you were burning. So how could we use an experiment to figure out what the formula is if we don't already know it? This was a really big deal until about the 1800s. They had real problems trying to figure out how many of each atom were in a compound. For a long time, people didn't know if water was HO or H2O, for example. It was argued about even as recently as a couple hundred years ago. Because they didn't know what the weight of a particular atom was. So if we wanted to figure out what the formula is for the compound, the first step is going to be to figure out what is the empirical formula. So empirical means coming from data. The empirical formula is going to be the formula from the data, and so from the experiment directly. It may not be what's called the molecular formula or the formula for the whole molecule. But if we wanted to figure out the empirical formula, let's say we decompose a sample of water like we're seeing here. And in this tube here, we weigh the gas and we get 3 grams of hydrogen. And we get 24 grams of oxygen. So how would we determine an empirical formula given this data that we have, that we separated water into hydrogen and oxygen? So here's the question. Decomposition of water from 3 grams. Find the or decomposition of water to 3 grams of hydrogen, 24 grams of oxygen. Find the empirical formula. We have to convert to moles. So what we're trying to figure out here with the empirical formula is, do we have 1 hydrogen atom for every 1 oxygen atom, or do we have 2 hydrogen atoms? So we have HO, or do we have H2O? Do we have HO2? So the first thing we got to do is get our numbers into a count of how many atoms. And how do chemists count atoms? They go for what? The mole. All right, go for the mole. So what we want to do is, for each of these elements, we want to use their molar mass from the periodic table to convert their grams into moles. Okay. So once we're going to divide the experimental mass of each element, the 3 grams for water, by its molar mass. So if we look at the periodic table, 1 mole of hydrogen is equal to 1.01 grams of hydrogen atoms. Okay. So we put the 1.01 grams of hydrogen atoms on the top so that they will cancel. And then we end up with moles of hydrogen atoms. So this gives us 3.0 moles of hydrogen atoms. Now, if we go and look on the periodic table for oxygen, 1 mole of oxygen is 16 grams of oxygen, atoms, not molecules. That's very important, like on the lab. So the grams here cancel. If we put the 16 grams of oxygen at the bottom, we get the moles of oxygen, 1.5. And so remember, we're going for the mole because that's the easy way to count atoms. So we don't have to worry about counting them all individually. Look at these nice numbers we get, 3 moles instead of saying, 9.06 times 10 to the 23rd hydrogen atoms. It's much easier to say, oh, 3 moles of hydrogen atoms. Okay. So you might be able to tell right away, we have twice as many hydrogen atoms as we do oxygen atoms. The way we formalize this is we write an empirical, so yeah, 3 moles of hydrogen for every 1.5 moles of oxygen. So the way we formalize this is we start by writing the numbers next to, like we would for subscripts for a molecular formula, but we have one more step. We're going to divide by whichever number is the smallest. So in this case, the smallest number is 1.5. So we're going to divide the 3 by 1.5 and the 1.5 by 1.5. And 3 divided by 1.5 is 2, and 1.5 divided by 1.5 is 1. Oh, good question. Why was hydrogen, so the molecular formula, or the empirical formula for water we can see here is H2O, and that happens to be the molecular formula. So the question is, why did we use 1.01 instead of 1.0079 or 8 or whatever? What I did was I rounded here to 3 sig figs. So since this was an 8, I rounded this 0 up to 1.01. Remember, when you're looking at periodic tables, there may be lots and lots of numbers here. So you get to pick, as long as you don't pick too few, you get to pick how many you're going to use. If your data that you're starting with has 4 digits, you probably should pull 4 digits. But here we didn't really need them to figure out the molecular formula. But like, for example, I'll show you. If we go to hydrogen on Wikipedia, and we look at the molar mass, so it gives us 1.00784 or 1.00811. There are actually 2 of them, depending on other things. So we don't have to use all these digits. We can use fewer of them. But some periodic tables have lots and lots of them on there. But you wouldn't want to write them all down every time because you don't always need them all. So that's why in this case, we only chose 1.01. We thought going 2 after the decimal is probably good enough, and it was for this case. If you're in doubt, just look at whatever data you're starting with. If you're starting with data, like here we started with data with 2 sig figs, make sure you get at least 2 sig figs. So we want to at least have 1.0 for hydrogen, but 1.01 is probably better. But that's a great question. Any follow-up for that? Oh, you're welcome. So sometimes it's possible that you will get fractional subscripts when you divide like this. So if you do get one of these fractional subscripts, so here, for example, when we divided, we got an, whoops, I went back too far. When we divided here, we got whole numbers. 3 divided by 1.5 is 2. 1.5 divided by 1.5 is 1. But what if we got like 2.5 or something? In rare cases, that can happen. If you divide like we did there and you get 0.5 for something, multiply everything that you have at the moment by 2 and so forth. I'm not going to give you a problem that's that hard, but that's just some general info for you that they tell you in the book. Finally, if we have the mass percent, can we get the chemical formula? So an the thing is that about empirical formula, the problem is that it tells you basically the whole number ratio of the atoms. For example, H2O tells you there's twice as many hydrogens as oxygens, but you can't be certain that there are only 2 hydrogen atoms in the molecule. So what we want to do is use the empirical formula to get what's known as a molecular formula, which will be a whole number multiple of the empirical formula. For example, hydrogen peroxide, which is usually dissolved in water and you put it on your cuts or whatever to clean them, that has a molecular formula of H2O2. So its empirical formula is actually HO, 1 hydrogen atom for every 1 oxygen atom. But an actual molecule of hydrogen peroxide has 2 hydrogen atoms and 2 oxygen atoms in it. So if we get the empirical formula for hydrogen peroxide, for example, HO, how can we get the, so we want to know how we can get the molecular formula from that. So I'm going to give, the molecular formula will be the empirical formula times N. So in the case of hydrogen peroxide, N is 2. HO times 2, if we double the hydrogens and double the oxygens, we'll get the molecular formula. So as I said in the last slide, the molecular formula is a whole number multiple of the empirical formula. Let's say we have this empirical formula, CH2O. Okay. What we want to know is we want to know exactly how many carbon, how many hydrogen, and how many oxygen atoms we have in this molecule. Yes, we know from the empirical formula that there are twice as many hydrogen atoms as there are oxygen atoms, but how many is that? How many total? Okay, we need to figure out N, basically. So here's the way we figure out N. If we take the molar mass or the formula mass of the empirical formula, and we multiply that times the multiplier N, we'll get the molar mass. Or in other words, N will be the molar mass of the whole molecule divided by the empirical mass. Now don't try to memorize this. Instead, think about what it means. If there are exactly twice as many atoms in the molecule as it looks like in the empirical formula, then the molar mass for the whole molecule will be twice the molar mass for the empirical formula, because there are exactly twice as many atoms. So that's why we do molar mass for the whole thing here divided by the molar mass for the empirical formula. So here is fructose. Fructose has this empirical formula, CH2O. And the molar mass for fructose is 180.2 grams per mole. So what we need to do is we need to figure out what is the molar mass of the empirical formula and see how much bigger is the actual molecule compared to what's written in the empirical formula. So the molecular formula is going to be a whole number multiple of CH2O. We need to figure out what that multiple is. So, given from the last slide, this was given to us. Molar mass of fructose is 180.2. Also, the empirical formula is CH2O. If we know these two things, can we get the molecular formula? Well, to get the molar mass for CH2O, it has 1 mole of carbon atoms. And from the periodic table, those weigh 12.01 grams. These are grams. For hydrogen, there are 2 moles of hydrogen in 1 mole of this. Each one weighs 1.01 grams to 3 sig figs at least. And there's 1 mole of oxygen atoms, each weighs 16 grams. So the total molar mass for the empirical formula is these added together, 30.03 grams per mole. Now our goal is to find the multiplier. How much bigger is 180.2 grams compared to 30.3 grams? So we're going to now divide 180.2 over 30.3. So 180.2 grams per mole, the mass of the whole thing, divided by the mass of the empirical formula, which is really just the whole number ratios of the atoms, not all the atoms, right? The molecule is exactly 6 times bigger. If we divide 180.2 over 30.03, we get about 6, meaning that, yes, we have twice as many hydrogen atoms as oxygen, but those hydrogen atoms are 6 times 2, 12. Those oxygen atoms are 6 times 1, 6. So ultimately, we use N to find the values. It will be carbon 1 times 6, that's 6. Hydrogen 2 times 6, that's 12. Oxygen 6 times 1, that's 6. Okay. And so you'll be given, in a problem like this, you'll be given the molar mass of the molecular formula. You'll have to add up and figure out the molar mass for the empirical formula. Then you divide the molar mass of the whole thing by the molar mass from the empirical formula to get how much bigger is the real molecule compared to the empirical formula. Did anyone want to ask a question about that example? Okay, guys. Well, that's it for the Lesson 16 lecture. I do want to tell you what to do next. So I got you started on the lab. So going back to Canvas, if you want to look at the slides for our lecture, I'm going to move these above the experiment actually. So the slides are here and the problems associated with the lecture I just gave are right here and they're worth 19 points. The experiment that we talked about today is here to download. You'll upload it here when you're done. I have a due date April 7th, okay? So that is a week from today. I'm giving you quite a long time to do it, but I do want you to start on it as soon as possible. Hey, you should be able to get it done in the lab period today. I know I lectured kind of a long time, or at least close to that. So that's what you should be doing next. These are your assignments until next time. To do Lesson 16, you do have to be on McGraw-Hill Connect. Right now, I have only, let's see, 17 out of 26 enrolled. If you're not enrolled, on the experiment, how do you get to the atoms? Okay, if you want to go from moles to atoms, your conversion factor, let's see, let's go back to the slides. Oh, I closed them. I'll point out to where you can look at on the slides. And you can always ask me questions. Please don't be afraid to ask me questions, guys. I know we're not in the same room, you know, and it's harder, but this is, I mean, I'm here for you guys, all right? Just ask me a question. We can get on Zoom. We could just email or whatever. So if you want to go, first of all, if you want to get the atoms, you need to have the moles. Always go for the moles first. then once you've got the moles, okay, you can get to the number of atoms or molecules or whatever. Now, there is one extra step. If you have the number of moles of the molecule, or the number of particles of the molecule, but you need to get the atoms inside that molecule. An example is right here. So let's say I already know how many moles of calcium chloride I have, but I'm asked how many oxygen atoms are in the calcium chloride. Then I need to look at the formula and see, oh, if I have one of these, I have 4 oxygen atoms in it. So if I have a mole of these, I have 4 moles of oxygen atoms in it. And so there could be one extra step there. And again, if you want to go from moles to how many, moles of anything to how many, the conversion factor between moles of something, moles of something and how many is Avogadro's number. A mole of anything is this many of them. Oh, the file tab. Oh, geez. Yeah. Sorry, if you want to go between moles of something and how many, it's always this many is a mole. So you can kind of use this as a guide. The moles are the center. So you can go from mass to moles using the molar mass. You can go from moles to number of particles using Avogadro's number. The only thing that's a little extra step is if you've got moles or number of particles for the compound, but you want the atoms inside, for that you have to look at the formula and figure out, okay, if I have one of these, how many oxygens are inside of that? Oh, well, each one of these has 4 oxygen atoms. 1 times 2 times 2, 4 oxygen atoms. And each mole of these has 4 moles of oxygen atoms. And so you put the moles of the whole thing on the bottom here, and the moles of the oxygen atoms on top. That gets you the moles of the oxygen atoms. So did you want to follow up on that? This is one of those things that takes a lot of practice. And so I do have some problems like this. And you can also refer to the section in the book. So if we're going here, to your assignments. So lesson 16. So I have going from moles to number of atoms. These are, the first ones are on the easier side, but they get harder as you go along. Moles, numbers of atoms again. Going between a mole and a dozen, or these are various different conversion factors that are like a mole. And this is also going between a mole and how many grams. And then if you do want to go to where this is in the book, you can go to review here. And of course, you always have me. I just want to tell you, what kind of resources you have if you want to use those too. You can always go into the book there. And hopefully, I don't know if you have a physical copy of the book, but you at least have this. And so you can go to where they talk about these. And look at a few more examples here. I hope that helped a little bit. You're welcome. So I've got lots of problems for you to practice on this. If you've done them all and you still feel like you're not confident, let me know. And then before the next exam, I'm going to do another review assignment, basically extra credit review assignment. Okay, I'm glad the lectures are working for you. In some ways, it's kind of nice because I'm on my own computer. I can very easily show you all these resources that I have. Whereas when I'm on the school computer, it's not quite as convenient. Okay, So I'm going to wrap up the lecture for today. Again, do not hesitate to contact me. You just send me an email. We can set up times to meet just like this anytime you need me. Maybe except for Saturday night. Maybe I'll play some StarCraft or something. You guys have a great afternoon, and do the best you can on the assignment. Let me know when you get stuck. That's where I'm really going to rely on you. You got to let me know when you get stuck so I can help you, because I can't look at you and see when you're stuck. So, okay, let me know. And I'm going to stop the recording and I'll put this up on YouTube as soon as I can. You guys have a good night.